Okay, now it's recording and transcribing. So that's good. And I see this red dot here. I can also see myself speaking and being transcribed. Anyway, but thanks for taking note of that. Let's get back to Colab. So a good thing with Colab is that you can execute some of the Linux commands. So some of you might have tried conda install xtb. Sometimes it works, sometimes it will give you segmentation for depending on your system. Conda is not the most preferred. It's easy, but it's not the most preferred way to install xtb. Sometimes I've been able to worked with it on different systems. Sometimes it's very easy, sometimes it's not. So I prefer that I would suggest that you, for example, download it from their GitHub, a precompiled binary. Well, it comes as a tar file. It's a compressed file. You untar it, and then you have to set up some of the environment variables. So here, when I'm downloading it, it goes to /content/ xtb this folder when I unarchive it. If you do it on your local machine, you can do the same. You can do it the same way. Instead of wget, you can maybe just download it using the link manually, and then you untar it, and then that's there. But you will still have to set these variables so that the system knows what is xtb home. When xtb is executed, it needs to know what is xtb home variable. And so wherever you have stored it, it needs to be on your path. If you're not sure how to do it, just look up how to add an environment variable in your Windows machine. And you can find many options on the internet that you can go and do so. If you still get struck, let me know. I can try to help, but different machines can have different kinds of issues, so it can sometimes get challenging. But also see it as an opportunity to learn a little bit more about installation and working with different kind of operating systems. So the xtb home, it said that okay, this is where xtb resides, and I have added this to path so that any executable file like xtb, it's an executable. You just execute it on the command line, it runs. The system knows where to find the executables. So whenever I try to, if anywhere in the system I type the xtb command, it will look for everything that's on the path. And if it finds that, it will execute it. This is kind of universal for all operating systems. So I'll run it. So see, it has downloaded, and now it is opening the compress file. Lots of files. Now I have added these variables, right? So I will simply run. Which version of xtb am I using? 6.4.1. You might have a different one. And then I will also install ACE. ACE is Atomistic Simulation Environment. It provides you with some very useful libraries, mainly in Python. You don't necessarily need to be an expert in Python, but it's good if you know a good amount of, if you're familiar with Python, it helps you with, it makes life very, very easy. But for using it, you can always look up, for example, these commands, you can just copy paste and try to use it. Good thing with Colab is also that you don't need to set up the Python and everything. It's all there. So that's, but there are also some problems because you can sometimes get version conflicts and everything. So it's not always just plug and play. More like plug and pray sometimes, but it works. It's a good thing. So I'm going to install pip install ACE. So it will install that Mystic Simulation environment in the. So it gives me a very good way to sort of manipulate, generate molecules, manipulate. It's also lots of databases. So if I want to generate a surface or something, I can immediately do it with, most common surfaces. I can immediately do it. There's also a database of molecules. So what I'm going to do is I'm going to call some of the functionalities of this library. I'm going to call the atoms object, which is a particular way of reading and working with atoms. I'm also, there's this build ace.build module from which I'm importing a molecule. So if I say later on, I'll say, okay, get me a molecule H2O, it knows what H2O is. And I am also using the visualize so that I can visualize it in the Colab. The visualization options are limited, but they can be very powerful. Then there's also an optimizer, BFGS. It's not, when I say optimizer, optimization is a classical, it's a common problem. Like, you essentially set up like a function and put up some constraints that you want to optimize for. And there are different algorithms to or implementations to set up the optimization. BFGS is one of them. So this is inbuilt and it depends on what kind of calculator you are using in ACE. And then the next session, I'll also try to give you more feeling about ACE. Today, I'm just trying to give you a bit of exposure of, okay, these tools exist. We can do some chemistry with it so that you can play around on your own as well. And then I'll put some more plotting and like, libraries. And here, this is an important part. I'm trying to tell Colab that, hey, you can use my Google Drive as storage. It will ask for some permissions. Ask for a lot of permissions that you have to provide. Continue. See, it has some 9 services. Continue. So it's now connected. So now it can access my Google Drive /content/drive/my drive. So anything that's on my drive, I can also access from here. I have defined a functionality to also download certain files. That's just a handy functionality. Now what I will do is I'll create a directory. So when you open Google Drive, my drive is where you usually land. This is like your home for the Google Drive. On top of that, I'm making lecture1/xTB. This folder already exists. That's why I have done mkdir-p, which means if it exists, don't give me an error, don't overwrite it. But if it's not there, create it in a nested manner. It will create all of it. Let me show you what this looks like. So this is like, this is my drive. I go to lecture 1 and I have xTB. My drive, lecture 1 xTB. I'll close it. Not really need it. So it made that directory. Then I say that this is also my working directory. This is just a variable that I'm setting for myself so that I don't have to type the entire thing every time. Now I say, okay, create a water molecule. Now it has created an object. You cannot see anything right now. But what I'm saying, okay, you have created this object in the memory. It's there. Write it in the working directory to a file called water.xyz. And now I'm saying, okay, show me the contents of this. See, it has water.xyz. It also has some other files because I was running, I already did some calculations. What I will do is rm-f web / I will remove water.out. Yeah, the good thing is the Gemini will already make some suggestions. I'll remove some of these files. Then I'll execute this command again. Actually, I can also execute it now because it will now assign number. See, this is 12 and this will be 13. So it is executed after it, and you see some of the files are missing. That's enough. I think you should also always remove the xTB restart if you don't want to restart the calculation. xTB restart is also gone. So now I will switch to this working directory. Some people have dropped out, it seems, but yeah, is a question. I can't able to. Can other people also not see my screen?
The screen is visible, sir.
You can see it, right?
Yes, sir.
Okay. Cool. Good to know. So I will now switch to this directory. Now this becomes my working directory. If I do ls, I will find some of this. Earlier I was doing show me the contents of working directory. Now I am showing simply show me the contents of directory where I am currently in. Then I want to run xTB calculation. It's simple. It's the command that you have also saw in the web app. Did a calculation, normal termination. Now it generates some more files. See, there are some more files. It also generates a vibrational spectrum file that you can also inspect. What you can say is cat wave spectrum. and it will plot out. See, it has 3 modes. 2 of them are the OH bond modes, and this is the bending mode of the angle. And I say that, okay, show me the geometry. You can also see it in the browser, but you don't have more functionalities like, getting the distance or something, or at least I don't know, maybe they're there. No, I don't think they're there. Oh. Okay. So now what I'm going to do is I gave it a good geometry because in the database, there was a decent guess of the geometry. What I'm going to do is I'm going to give it a distorted geometry. Now, I have already provided you a lot of theoretical background, so I don't want to muddle your head with any 3D geometry. But what I'm going to do is, ideally, this number should have been sine theta by 2, so that just so you know. So I'm just distorted the angle such that you see, if I run this, yeah. So you can see the angle is quite small, right? If you look at the water molecule here, it's close to 104.5 degrees. This is quite small. We all agree on that. Okay. So I'm going to give this, make a directory called distorted water. And there I will write water.xyz because I have created this file here, water. So I created the XYZ string. For larger files, you will have to do it differently. But here I'm just making a small file. I have read this into XYZ data and read this into a molecule object. And then I have written this and want to go to this distorted water directory. So I am here now. If I ls as in list what is inside, I already did some calculations, so some stuff is there. Maybe what I will do is rm minus f. Okay, this is the problem with AI. So you see, it asks me to remove the same file multiple times. Okay, so it has removed now. Now let's do a calculation. Again, the ls. So again, there is vibrational spectra. So now you see, I started with this geometry, and it landed me with a well-optimized geometry that it should be. Now what I want to do, now I've shown you a basic working of how to work with water molecule, but that's a little bit boring, right? Now I want to show you how to do a potential energy surface scan. So I showed you earlier about what a torsion angle is. So you have 4 atoms and you can like sort of change the dihedral angle between them. Similarly, if you think of ethane molecule, you have 2 CH3 moieties and you can rotate them around each other. And there will be a potential that will block that rotation, or that will there will be a potential energy associated with that rotation. So I will make this directory, switch to it, and then I'm using this function that will be very useful for you as well. What you do is you go to write file. You essentially can copy this. You have to provide the path where you want to write this file, and you need to provide this string. Just copy paste your XYZ coordinates, and it will simply write that file. Alternatively, you can also use an upload function where you can upload to the drive. I have not used that, but that's also handy. Instead of download, you can also do upload to a particular directory. But for now, we'll use this. So you see, it has written, it actually overwrote because this was already there, ethane.xyz. Now what I will do is, I will say, I want to view this file. So instead of using my brain a lot, what I'll simply do is view. Instead of water, I will say read. So it will now read this file. So it creates like sort of an AS object which can be directly visualized. So you see, we now have an ethane molecule, right? Are you guys following till this point?
Yes, sir.
So it's okay. And now what I will do is I will do a simple optimization first so that I have an optimized structure. So it's running, takes a little bit longer than water, and I can ls it and see I have some of these files already present here. If you look at this is the present working directory. I also look at the last 100 lines. So you see it has done the Hessian calculation. It also did, with the help of Hessian calculation with the vibrational frequencies, it again calculated the thermodynamic properties. We can do that. And then it gives me the total energy, enthalpy, and everything. If I look at, I have some of the files here. What I will now do is I will scan the bond between 8, 5, 1, and 4 moieties. So what are 8, 5, 1, and 4? How do I show you that? So 10 equal to read. You can also read xtb op.xyj. Get chemical formula, get chemical symbols. You can use this. So you see, you have how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms. What I'm saying is that this is 8, 7, 6, 5. So HC 1 and 4. So I'm essentially taking like four of these atoms, which are CH and CH moieties, and I'm trying to rotate them together. So essentially selecting 4 atoms, defining a dihedral angle, and I'll rotate them. What I'll say is I'll write a file called scan.input. And all of this is available. So, you don't have to put it in your brain. You can just copy paste this, try to see how to create it. I'll put some of the parameters. You can leave them unchanged for now. I'll say that, okay, the dihedral angle, initial dihedral angle is 60 degrees. You scan it from 60 to 420 in 72 steps. This is what I'm going to ask it. And what I'm also going to do is RM minus F xTB restart so that there is no problem anywhere. So this time it did not produce output because there is another command here. So the scan.inp file is written down. Okay, I have done that before as well. So now I will run the scan. So I see that it's an optimization run, but the input comes from scan.inp, which means it will do 72 geometry optimizations by changing the dihedral angle slowly from 60 to 420. Let's do that. Now I want to download this file. So let me put it xtb scan.log. And what I will do is I'll start my terminal. Let's xtb scan. So it's here. I will visualize it with no, it can be. So if you want to visualize it with ACE, you need to say that it's an XYZ file. Otherwise, ACE does not seem to recognize it for some reason. So you have to just rename it and say that it's an XYZ file. So you see, this is the ethane molecule. And it has done from 0 to 71, so essentially 72 steps, and I can play it. See, it's rotating now, right? So we are essentially changing the angle, the dihedral angle, such that the molecule starts to rotate. Now this rotation, it doesn't come free of cost. There must be some kind of potential energy change that's going on, because when you are rotating it, you are not at the minima of your energy. You are changing. You are essentially changing the geometry along one particular coordinate. That means there will be a potential energy penalty that you will, or potential surface that you will traverse. So I have defined a function here. You don't need to bother. You can just use it as is for it. But if you study it a little bit more, you will you will see that there are certain subtleties. And what I'll do is, what this function does, it takes xtb scan.log as input. And if you open this file, so what I'm going to do is head minus 20 xTB scan.log. So I'm reading the first 10. So every second line. So first line is number of atoms. Second line gives you the energy. So this program, this Python function, it essentially grabs that amount of energy. You can also use something else. If you use a more decent visualizer other than ACE, ideally ACE should have also done it. It will automatically read the energy values from the scan file. Anyway, what I'm doing is I will use that function to extract the energy and I'll print it. See, this is what. So when the angle is 0, scan step, this is when the angle is 60 degrees, it's at the minimum, then you scan it, it goes up and then finally goes down. And so, it traverses like, I think this step, all of this is equivalent to what this goes to 420. So 60 x plus 2x plus 3x is 420, 360. This is like 120, a step of 120. Every time you achieve a minima because of the symmetry of the system, and then again you get a potential energy penalty to go from one structure to another. Ideally, when you couple it to a temperature bath or when you heat up the system, it will be able to this mode of vibration. You will be able to place some channelize some energy into it, and it will rotate. It will also vibrate. The bonds will also vibrate. But this is like one particular thing that I have taken and essentially shown you how to do a scan. I'll stop sharing my screen now.